Good morning, everyone. Mr. Zatola here, looking to go and continue our radioactive decay piece on geologic history. Today, I want to look at the radioactive decay chart, but by mass. I have another video for percentage. By mass is a little bit different. So, building the chart. Building the chart looks almost the same. Our first column is going to be half-life. Okay. All right, half-life number. But now we're going to have our parent daughter, and this is going to be by mass. So usually it's grams, it could be anything. It could be kilos, it could be pounds, it could be whatever. And finally, our last one is still time, and this is years. And just as a heads up, if you watched, and I'll do it here on this one, but if you watched the other video already, you know that time is really dependent on your isotope. So we're going to talk about that further and later on. So building our chart, we're just going to break it up into some pieces. Again, I'm going to do like a dotted, because we have to know what's going on there. So half-lives always start with 0, 1, 2, 3, 4, and we'll just go up to 5 on this one. So let's look at 0. So here's the deal. When it comes to mass, it's all about what the question is giving you. They will tell you a mass if they're asking you what has happened over time by mass. They'll either give you a starting mass or they'll give you a mass at a certain half-life time. We'll talk about that. There's a way of figuring it out, but you'll know it's mass. Your mass units, grams, kilos, pounds, things like that, tons. So I'm going to start with a number that's just going to be easier for us to deal with. They can give you any number. That's the key here. Let's do 528. All right, let's just say, for this example, you start with 528 grams of parent isotope, and they want you to break it down, and you're trying to figure out how many grams are left, either parent or how many are now in daughter, at a certain half-life number. So like we started last time, whatever you start with starts as 100% of the parent. So there's no grams of daughter here, and 0 time has passed, because half-life, and we're going to talk about this, when you're 0, your 0 time has passed. No time's passed when you're born, and that's what we're talking about, when this isotope has started to decay. Okay? Again, I'm going to leave time alone until the end of the video. So let's just focus on the first 3 pieces here, and we'll do that. All right. Starting with our mass. So we know half-life means that half of the item disappears. It turns into the daughter. So how do we do that? So I'm going to bring up my calculator here. I'm going to show you how easy it is to do on the calculator. So let me make sure you can see it. So I'm starting with 528. And I'm going to divide that by 2. 264. So after one half-life, I have 264 grams of parent left over from 528. Slide this down. Which means, how much of my daughter do I have? Well, how I would do it is take the original 528 and I would subtract 264, which in this case, since it's the first one, is going to be 264 again. Remember, the combination of these two, if I was to add these two together, the parent and daughter, they will equal the original parent starting mass. So 264 plus 264 equals 528. Okay? Great. So put the calculator aside and let's take a look here. Now, after 2 half-lives, how much is left? Well, again, I have to take my parent, 268, and 268, and I divide it by 2, leaving me with 134 grams. Okay, sounds good to me. And you know what I did? I messed up. It's 264 and divided by 2. I knew that number was weird. It'd be 132 grams. Sorry about that. So yeah, 264 divided by 2 is 132, and I don't know how much my daughter was. I know I started with 528, so 528, and I subtract out 132. Yeah, 396. Okay, so 396 grams of my daughter now, right? If I was to add these two together, I'll get my original 528. That's the magic number, what we started with. All right, moving forward. After 3 half-lives, I'll take my 132 and divide it by 2 again. Now I have 66. Always double check. 66, great. And how much of my daughter? Well, I know I started with 528, and I will subtract out 66, which leaves me 462. And again, if I add 66 plus 462, I will get my original 528. That's the key. Right? We're always going back to that. Continuing. For our next half-life, just slide the paper up. 66 divided by 2 equals 33. Okay? So I'll have 33 grams after 4 half-lives of my parent isotope. If I started with 528 grams. All depends on what you start with. How do I figure out my daughter? I say 528 minus 33, and I'm going to get 495. And again, 495 plus 33 will equal my original 528. That's the key. Moving on. All right, don't be afraid of the numbers. 33 divided by 2. This is why we're using calculators, right? 16.5 grams now. All right. 528 minus 16.5. Again, I'm using 528 because that's what I started with. They could give you any number. So 16.5 plus 511.5 will equal 528. Okay, so that's how we do it based on grams, and I can't emphasize enough, it all depends on the amount they give you, all right? Whatever they give you goes here, all right? That's just how that works. Let's talk about time, and then we'll do one little complicated piece where you'll actually figure out the original mass after a certain number of half-lives. That's something they've done. So, all right, time. Time is isotope dependent, right? It depends on the isotope you use because if we go back to our reference tables, each isotope has a different half-life time, right? So let's just use carbon for this one, right? How do I do it? Well, I know C14's half-life is 5,700 years. I know that because I used my reference table chart, page 1, 5,700. I've learned to convert. All right, so real simple. 5,700 times 1. Only need a calculator for that. Years. All right. Now, bring in our calculator. I know what 5,700, so I'm using carbon times 2. 11,400. Same process for both charts. 5,700 times 3 for my 3 half-lives. It took 17,100 years to get there. And if I want to know how long it takes carbon to go to 4 half-lives, times 4, all right, 22,800 years, and so on and so forth. That's how we do it. We take our half-life number, we multiply it by the isotope half-life time. So again, different for each. This is only for carbon, these numbers right here, all right? If you would use rubidium, right? If we're using rubidium, we're talking 49 billion times the half-life number, right? So 0 times 49 billion is 0. 1 times 49 billion would be 49 billion. Okay. Now, let's get into a little more complicated piece about this. Let's say they tell you that you have, and let's use carbon for the fun of it, carbon 14, since we have our numbers here. and they say carbon-14. They don't know how many half-lives have gone by, but they certainly know that you have 66 grams of your daughter, or sorry, of your parent, and 462 grams of your daughter. How you would do that, you'd immediately take the two numbers and add them, and now you know the total. All right, 528. Sure enough, we know that because we have our answers here. So it'd say, how long did it take? How many half-lives did it take to get that 462 grams of daughter, or 66 grams of parent? And the easy way to do it is take the total number, divide it by 2, equal. Divided by 2, that's 2, equal. Divided by 2, that's 3, equal. And sure enough, there it is. It took us 3 half-lives to get there. I know I went through that fairly quick, but I would rewind it and double check it. It all depends. When we're talking about radioactive decay chart by mass, it depends on the original mass they give you. They'll never leave that blank. They'll always give you something there. All right, everyone. I hope everyone's healthy, and I hope everyone's doing great. Keep an eye out for more videos. If you have any questions, make sure you get in touch with me, okay? Thanks so much. All right, bye.